Today is the third day. Today we have our expert, Professor Balasubramanian sir from IIT Roorkee. Before going to start, it's my pleasure to introduce Professor Balasubramanian sir. Yes, Dr. R.Balasubramanian has built an extensive and distinguished career in academic and research, currently serving as a professor in the Department of Computer Science and Engineering at IIT Roorkee. That is from December 2018 onwards. He also holds the prestigious position of chair professor under the High Hub, the Evans Park Fellowship from May 2022 onwards. It's currently going on, and serve as a joint faculty and at Mehta Family School of Data Science and Artificial Intelligence from June 2021 onwards. Still, it is also going on. Professor Dr. Balasubramanian sir earned his PhD from IIT Madras, Chennai in July 2001 under the esteemed guidance of Professor K. Swaminathan sir and Professor Sukhandev Das. And an exemplary academic, he completed his MSc in mathematics from Madras Christian College, University of Madras in 1996. And his BSc in mathematics from AM Jain College, University of Madras in 1994. His academic journey has been marked by a consistent excellence and a passion for advancing knowledge. Dr. Balasubramanian sir has enriched his career with visiting position at a prestigious institution worldwide, including the University of Queensland, Australia, Osaka Metropolitan University, Japan, Kyoto University, Japan, Cotton University, Australia, and National University of Singapore. He has also engaged an impactful research collaboration with the institution in Italy, France, Malaysia, Canada, and US. In addition to his current role, Dr. Balasubramanian sir has previously served as an associate professor in the Department of Computer Science and Mathematics in IIT Roorkee, following his tenure as an assistant professor in mathematics. Earlier in his career, he contributed as a lecturer in BITS Pilani, worked as a postdoc fellow at Rutgers Universities and the University of Missouri. His global experience spans interdisciplinary research in mathematics, computer science, artificial intelligence, and cybersecurity. This breadth of extensive has enabled him to make a significant contribution to both academic and innovation. A testament to his commitment to education and research, Dr. Balasubramanian sir has supervised an impressive number of theses across the multiple academic levels. He has guided 32 completed PhD scholars and 15 ongoing, 55 completed MTech thesis, and 4 is currently going on. Actually, this numerical maybe is it's correct, but it is more than that, and BTech like that. This remarkable mentorship records underscores his dedication to forecasting research excellence, nurturing talent, and shaping the next generation of the professional and scholars in this field. Really, sir, we are very fortunate you will be available that means in this program. Behalf of myself and the coordinator and our director and ACT, we are warm welcome you, sir. Now over to you, Professor.
Thank you, Dr. Vaithiyanathan. I'll just share the slides.
Professor. Welcome, Professor. Good evening, Professor.
Evening.
Sir,
good evening,
welcome,
madam.
sir.
Good evening. So with your permission, shall I share the slides?
Sure,
you muted. Vaithiyanathan, you muted.
Yes, Professor, you can proceed.
Yeah.
Yes, until your voice and then slide flow, I'll be there, sir. No issue, sir. Please carry on.
Is it visible? My slides visible or?
1 minute, Professor. It is coming, I thought. It's not. Yes. Just go to the slides.
The screen is visible, sir.
Slide?
Yes, Professor. Yes, Professor. You can put it in the slideshow and move, Professor. Second, third slide. I'll look into that. Yes, Professor. Be careful. Yes, please, sir.
Yeah. Thank you. So thank you, Professor Vaithiyanathan and Professor Shelly, Madam, Shelly Sachdeva. Am I audible?
Yes, Professor. Yes, you are audible,
yeah,
Professor.
Thank you. Thank you. Thank you. I'll just. So very good evening, everyone. I'm talking about the biomedical imaging, medical signal or image processing. This is the title which was given. So the organization of the talk will be like this. So I'll have a basic introduction. Then we are going to see how skeletonization is going to apply in medical imaging. And then I'll talk about biomedical imaging. So under this, we are going to see brain lesion delineation and classification, where the data set of computer tomography, CT and MRI will be used, right? And then we'll see some medical applications. So skeletonization, right? It was the very old problem. So in which, suppose you are given, let us say, a 3D object, right? I want to handle the 3D object digitally, right? So even 2D object, right? So we have to normalize, right? So in the case of 2D image, we call it as a pixel, whereas in the case of a 3D data, we call it as a voxel, right? So during this process, suppose assume that I am doing voxelization, right? So 3D data I am handling. So, it is not very easy to handle 3D data, right? So in that case, so is there any possible way to compress this 3D data, whereas my topology should not be affected, right? So I should have my 3D object information intact, but at the same time, I cannot use this 3D data extensively, right? Maybe, the saving point of view or handling the data point of view or rendering, right? Or a processing point of view, all right? So in this case, the skeletonization play a vital role, right? And then we will see how the application of skeletons, right, which are useful in medical imaging or medical field. So this was the work done long back, almost 2 decades back, right? So when I was a postdoc at Rutgers University in New Jersey, so we have done, and I am going to use this application, right? So where if I use some of the medical imaging or medical data, I will do the skeletonization, right? So how we are going to do, so that we will see. So suppose, assume that you have a rectangular object like this, right? So how do I define a skeletal point, right? What is the skeleton of a rectangle? So the point that the line that you are seeing over here, right? So for example, pink in color. So that is the skeleton of a rectangle, right? The pink in color that you are seeing from here, and then this line, and this line. So this is nothing but a skeleton, right? How do you define a skeleton? So for example, if I call a point SKI, right, which is a locus of a skeleton, so that means it is equidistant, right, to the boundary point. I can find 2 points such that there is an equidistant. For example, B1 SKI is equal to SKI B2, so that we know. So when it is satisfying this, and then you're finding out all the locus, that means when I am finding, assume that I take a point here, I can always find an equidistance to the boundary, 2 equidistance to the boundary. Whereas if I select a point here, right, assume that I'm selecting a point here, I cannot find 2 equidistance. So this is not a locus of a skeleton, right? The locus in the sense the point that lie on a skeleton. So SKI. So like this, when I find, this is nothing but a medial axis in 2D, right? There's a medial axis in 2D. And in the case of a 3D, you call it as a surface, right? Medial surface. So now, where exactly the skeletonization is being used in medical imaging, all right? So here you can see the cerebral artery. This is called cerebral artery. And now you can find this is a central line, all right? So this is the central line that you are finding. So this has appeared in the literature, 2014. So here, this is the center line. All right, the one you are seeing over here is the center line. So now, what we are going to do, so given a 3D object, how to extract this curve skeleton, right? How to find out the curve skeleton. So that is the main aim, right? So because the object need not be like a planar one. So planar means we can always think of a straight line, all right? So any object need not be following the planar, any object, so that, I mean, the skeleton need not be skeleton. So therefore it call it as a curve skeleton. So that is what the main idea of this particular work. All right. So in the case of 3D, I can distinguish, this is a, suppose a cuboid or parallelepiped is given, right? I am finding out the medial surface. So this is the medial surface. So there exists a plane. Whereas here, this is called a curve skeleton, a skeleton, right? Yeah, you can also call a curve skeleton because it is not form an exact straight line, only one straight line. All right. So this is a skeleton. So suppose I have a cube or let us say parallelepiped. So this will be a skeleton. So you will have a line, right? So now, what is the use of this skeletonization? So as I already said, we can have the compact form, right? That is the main application. And it has several property, homotopy. So homotopy in the sense, because I said the skeletal point SKI, so it is visible to all the boundary, all right? The entire boundary will be visible from that particular point. So you call it as a homotopy. It is like a convex property, all right? If suppose you want to define a convex polygon, so we know that if I select 2 points inside the polygon, there exists always a line. That line completely lie inside the polygon, right? You call it as a convex polygon. So homotopy is also like this. And similarly, invariance under isometric transformation. Suppose I rotate or translate, right? This skeleton, the whole object will also be changing. That is what the idea is. What exactly in the virtual reality they are doing, right? So they try to find out the skeleton first and then try to reconstruct it. All right. This is called as the invariance under isometric transformations. Similarly, that's what reconstruction. From the skeleton, I can able to reconstruct the object back, right? So in the virtual reality, what they do, suppose a given object, 3D object, they find the skeleton and then do the movement, do the animation, all right? And then take it back, all right? Bring it back. That is called reconstruction. Thinness, the skeleton should be as thin as possible, right? So that means you are extracting the pixels or voxels, so which will be as lower as possible. Medialness, the meaning is it should be exactly in the middle, all right, of the object. 3D object is given, the medial axis should be exactly in the middle. Robustness, I request all the participants to mute the mic. Somebody open. Kritika and Kritika, can you mute your mic?
Participants, please mute.
Kritika K, because you are disturbing other users. Kritika K, is it possible, Dr. Vaithiyanathan, can you do it? If you're admin. Okay, thank you. So all the participants, please mute your mic. Thank you. Unless, I mean, if you have any questions. Okay, so the robustness. So the algorithm should be as robust as possible, because even if it is a noisy cases, right? Even if it is a noisy image or noisy 3D data, and I mean, you should, your algorithm should work. And visibility is another convex property, right? As I already said, the homotopy is nothing but the topology. The 3D preservation should be there. Suppose I have a 3D object, this is my skeleton. So the skeleton should follow the topology, all right? Whatever topology 3D skeleton has. For example, assume that we have a bone, right? So whenever we are moving our flesh, bone is also moving, right? So in that case, suppose I have a skeleton, the question is it possible to reconstruct the object? So that is a homotopy property, and visibility is the convex property. Already I said, right? So from that skeletal point, it is possible to view the complete boundary point, right? So that is what the meaning of visibility, the convex property. So these are all the properties where the 3D or 2D skeleton has. So now, how do you do this? How do you find out this 3D skeleton, right? So there are several ways. So one is a grass fire propagation, right? Then we have a thinning algorithm. Third one is Voronoi, and fourth one is a hybrid approach. So what do you mean by grass fire propagation? For example, assume that I have a I put the grass, right, the dry grass in the rectangular form, right? In the rectangular form, I put the dry grass. Assume that I'm firing up in the boundary point, exactly at the same time, boundary point. Imagine, right? You have a dry grass. You are firing it in the boundary points, right? Exactly at the same time. So then what will happen? The fire will move, right, towards inside, right? So towards inside, and one point of time, the fire from different directions will meet, right? The fire from different directions will meet. So when they are meeting, all right, I'm getting some distance. When they are meeting, okay, so you can find out the locus, right? When they are meeting, you can find out the locus. One second, actually, I'm getting some disturbance in the room. One second, I'll be joining. Sorry, I'll just continue. All right. So when the fire from different directions meet, all right, let us say we are taking those locus, those points. So those points will be nothing but the skeleton of that rectangular object. So this will be true for all the objects. All right. So you can imagine, right? What did I say? If you have a rectangular object, put a grass and then fire it in a boundary, right? So they will, I mean, two directions. The fire comes from different directions, will meet at one point. So take all those points and then plot it. So you will get a skeleton. So that is one way, right? Then several thinning algorithms. Suppose assume that you are given a 3D objects of voxels. So try to thin as much as possible. So that means you have to apply some algorithms, all right? And remove all the, let us say, starting from the boundary, I'm removing. I'm keep on going inside, right? And then as thin as possible, is it possible to get a skeleton? So thinning algorithm. Similarly, the geometry-based algorithm, right? Computational geometry-based algorithm is called Voronoi skeletons. And hybrid is a classification. I mean, hybrid is nothing but the combination of all the three or two, right? So you call it as hybrid approach. So now, this is basically the first one I said, it is basically a generalized potential function, all right? So for example, I choose, this is a parallel, this is the polygon. So in this polygon, let us assume that I am choosing the boundary points, right? And then I'll try to find out the skeleton, right? So how do you do this? So for example, initially you are given a 3D object, you do the normalization, you call it as a voxelization. In the image processing, you call it as a pixelization, right? So voxelization. So then mathematically, let us compute the generalized potential function at every voxel. Right? Then we will talk about this seed value. How do you compute the seed value? Then joining all the seed values will form a skeleton. All right. So the first step is trivial. We are going to normalize 3D object or 2D or image you are given. Basically, the digital image nothing but the normalized one. All right. Every coordinate you will find some gray level value. In a similar way, do it in 3D. All right. The second case, we start from the second case, how to find out the generalized potential function. So generalized potential function, which is nothing but the integration of ds divided by r power m. So where r is nothing but, right, so the potential at any point. So suppose if I consider, let us say, a point inside the voxel, right, and then assume that whichever is the boundary, right, the boundary is, let us say, r dash, right, the boundary is r dash. So for all the point r dash, one point I'm taking inside, one object I take, consider any point on that object, right, and then to the boundary point I'm finding out the distance, right. So to the boundary points I'm finding out the distance. So r dash minus r. So take the take the absolute value or call it as capital R. And m, we are going to call it as the order of potential, right? So when I generate this, say for example, in the discrete case, right? So in the discrete case, the potential phi, which is defined as 1 divided by Ri power m. Ri is nothing but the distance to the boundary pixel, right? Any object distance to the boundary voxel or pixel, right? And then I calculate, let us say, del phi, right? So del phi, which is nothing but the differentiation of Ri power minus m. So we will get like this, and the negative sign indicating that the potential move towards inside. Exactly, I gave the example of the dry grass, and then you are firing up the boundary points, right? You have a dry grass firing up in the boundary points. So this is exactly a potential field. The example that I had given, physics point of view, it is called the potential field. So you are calculating like this, right? So once you calculate this, your potential or vector field, right? So once you calculate, let us say, gradient vector, the gradient vector look like this, right? For example, this is a chess piece. You are getting the potential, or this is a good example. So this is the object, and this is your potential field, all right? Gradient vector, right? Here you can see, suppose I am asking you what is the skeleton of this object, right? So here you can see it is forming. Suppose you are lightening up the fire in the boundary. You have a big boundary, right? So it will go, for example, the fire will go in this direction, and from here the fire will go in this direction, and they meet at a point. You look at this. This is the skeleton, right? The one you are seeing over here is nothing but a skeleton, right? So this is a case. For example, this is a rectangular object. This is what the example I had given. The boundary point, you are firing it up, and they all will meet at this point. So this is what the skeleton we had seen, in fact, initially when I defined a medial axis, right? So this is how we are finding. For example, this is the M letter object, and you can see this is a skeleton. So the vectors from the different directions are converging, or the fire from different directions are meeting at a point, right? So this is based on the potential function. And then now, I mean, leave that application point of view, I can able to find out the skeleton, right? So here you go. This is a 3D object or 2D object. You can find out the image. You can find out the skeleton, right? So for example, here you can see the skeleton. So now extract this. I mean, visually we can able to see. Suppose you are given a 3D object, digitally you have a 3D data. How to extract that, right? So for this, you calculate, find out the I curvature boundary points, curvature, 3D object, eye curvature, and high divergence interior point, and then the saddle point, right? So for example, so in this case, you call this as a bounding seed points, boundary points, and then these are all the high divergence points. All right. So for example, here, one direction from this side, second direction, and the third direction. From three directions, fire are meeting. Right? Three directions, the fire are meeting. That is why it's called a high divergence. Whereas if you take point here, right, assume that I'm taking a point here, only two directions of fire will meet. All right? The physical meaning I'm saying. There are points, two directions, fire will not meet. For example, if I take a point here, I mean, fire is going in this direction only. In two places, it won't meet. Right? So here, if I see two directions, but whereas here, it's more than two directions, I can say. All right? For a safer side, I can say more than two directions. So this side, one, this side, second, and the third, this side. All right? Whereas if you look at critical point, I mean, in many directions, from many directions, the fire are meeting. All right? I can give more than three. One from this direction, second from this direction, third from here, and fourth from here. Right? So that is called the critical point. The critical point will exactly lie in the middle of the object. Exactly the middle of the object. So we call it as a critical point. Right? So this we have to calculate. And high curvature point, we know there's a mathematics. You have a, suppose assume that you have an object. I can always find the high curvature. All right? Whereas high divergence and saddle, we have saddle. Middle point is a critical point. You call it as a saddle point. Right? So how do you find out the high curvature point? For example, assume that the G vector is a gradient vector. I have the Asian matrix. Right? So which is nothing but the gradient vector G, you have Bx, By, Bz, and I am differentiating one more time along X, Y, Z. So if you look at the Asian matrix, H is Bxx, Bxy, something like that, right? So this is the Asian matrix. So from this Asian matrix, all right, and if I am allowing this Asian matrix rotate in the x-axis or first axis with the gradient, so I'll get this, and this HT matrix, H dash matrix will be like this. So from here, I have the second derivative in the gradient direction. You call it as BGG. This is the one. And then HT dash is nothing but the 2D Asian. All right. So this is the 3D Asian matrix, and this is the 2D Asian matrix. So now your eigenvalues and eigenvectors, so which will be useful, find out the curvature. So whichever be the higher eigenvalue, you call it as the eye curvature. All right. Because the expression says like that. Similarly, critical point. All right. So critical point, we can find like this expression. I'm not going in the detail. All right. So it goes like this. It is based on the attracting node and saddle point. So attracting node, just like I said, in all the directions of fire will meet. Call it as the attracting node. Whereas saddle point, some of them will deviate. All right. So the one you had seen here, the critical point. So which is, as I said, physical meaning. So many points are meeting, right? The many directions, the fire are meeting. From mathematics point of view, it's an attracting node. So you can see the arrow. Whereas in the saddle point, some of them will diverge. For example, here this is diverging. Even here also it is diverging, one convergence. You call it as a saddle point. All right. So once you find this, for example, here I have the M object. So here you go. This point is called as a critical point. All right, the one, because in many directions, from many directions, the points are converging. Right. So then once you find out these saddle points and critical points, the remaining part of the algorithm is to join these points. Right. Right. So once I have done, assume that I have joined all these points. So now I can have, right, based on the applications, I can have 3 levels of skeleton. So one is the first level, assume that I'm joining only the critical points. And the second level with the skeleton, including the eye divergence point. And the third level, including the boundary point. For example, suppose this is a 3D object, you can see the level 1, level 2, level 3. All right. So level 1, you can say that, all right, I am joining only the critical points. It's almost like a best skeleton. And the second one, you are also joining the high divergence point. And the third one, right, you are joining the boundary points also. So depending on the application, so which application I am going to use, right? So this is another object. This is a case of a noisy case. Even though I said the algorithm should be robust. All right. So this is the way. So suppose there's a 3D object is given, how you are finding out the skeleton, right? So you are depending on how eye curvature points you are choosing. For example, I'll choose the top 1% eye curvature. This is the resultant skeleton. When it is top 1.5, skeleton is differing. 2, greater than 2, it's not so good, correct? So assume that you are given a 3D object, I am finding out the skeleton. So the last one is the colon. For the colon object, the medical imaging point of view. So I can able to find out the skeleton using this algorithm. So now I am coming to the medical imaging point of view, the same, similar or same objects, right? So these are all the object and the corresponding skeleton, okay? And in the case of a 2D, this is a skeleton. And in the case of, let us say, yeah. So now assume that a colon is given to you, right? 3D, right? It's a medical imaging colon. So here, I mean, as we know, right, when you are sending the angiogram in the colon, through colon, so we know that it has to pass through the central line so that the camera will capture what is going on, right, in the boundary. Correct. So it has to detect the complete boundary, right? If there is any problem with the patient. So the main idea is, right? So here the colon, the tubular object. The tubular object is given, and my main aim is to find out the central line, right? You call it as a skeleton. So that is one sort of application. I mean, we can use this skeletonization in medical imaging. And second one is, how can I stretch the colon, right? For example, the colon is given, the left-hand side colon is given. I want to stretch like this, right? I have to do virtually, right? Stretching, yes, of course, it is not possible, right, inside our body. So now, once I have this information, so is it possible to stretch the colon, right? So how do you do that? For example, visualization point of view, virtually, this is the given colon. So is it possible to stretch the colon, right? For many reasons, for many medical reasons. Correct? So here you go. Suppose I have the segmented colon MRI, right? Segmented colon MRI. This is the thin skeleton. It's a straight line. The skeleton that you are seeing here, right? The line, only the line segment when you see, this is the skeleton. This is the line segment. All right. So this is the line segment. It's a thin skeleton. And this is the thick skeleton. All right. And we are not worrying about the thick skeleton, but I'm giving an example of a thick skeleton. All right. So let us assume I do a line skeleton. You can also do curve skeleton. I have explained curve skeleton. So here, this is the colon. I am finding out the skeleton using the line segments. It goes like this. So this is a skeleton based on the algorithm that we define. So let us say, if you are taken, assume that the part of the skeletons, part by part, right? Assume that we are taking a part by part. So then it will form the line segments like this. The line segments are nothing but a skeleton. So now, given this 3D medical image, the colon, I am finding out the skeleton. Now I can stretch this line very easily. Different colors I have mentioned, and I can stretch like this. This is the one. So after stretching, right, I am reconstructing the colon possible. Right, that is what I said when I'm talking about the algorithm reconstruction. So we can always reconstruct. So reconstruction. Right. So then you can see your resultant data set. Right. So in the 3D point of view, this is the one, your colon, given colon is like this, you have stretched this. So now I can able to, if you are a medical doctor, you can able to see that. I mean, what are all the information that you can get very easily. For example, if I work with this colon, it's very difficult, right? What is going on here? For example, I want to check something over here, right? So you are stretching the colon virtually, and then you can able to see. So for this, skeletonization is being useful, right? So similarly, you can, and also we can slice it, all right? So since this is the stretched colon, and assume that I am slicing it. So for example, you have a data set of 991 into 90 into 94, right? So assume that in the Z axis, I can able to slice as a 94 pieces, assume that, all right? The digital pieces I can able to do. So one such case, you can see the slice, right? So now you can get more information about that colon, right? So that is what another application. Similarly, so whatever I explained over here is the straight line, all right? Straight line segments. So you may ask the question, so can we form, right? Can we find out the curved line? Yes, that is what the algorithm I explained. You can always find the curved line. So the red color, you have a colon, and then you can see the red in color, right? The red color you can always find. So in fact, I have this animation right now. I'm out of Roorkee. So somehow I forgot to copy those two. In fact, this is the one video. Maybe I'll send it to Professor Vaithiyanathan, and then he will share both the animations. So this is the colon. So this animation will tell you, right, after using the skeleton, it will be stretched. All right. So this animation I'll definitely send you, or I'll put it in my website. Okay. So this is the one. This is a colon, right? And when you want to stretch it, find out the skeleton, and you can stretch this one, right? This animation I'll send. And similarly, this is another animation where inside the colon, this red line will pass on to the central line, right? So these are all the important applications that you can find in the medical domain with the help of skeleton. Right? So these are all the advantages. So the joints will be easily identified, the topological joints. So that means we named it, right? The critical points, saddle points, high divergence points, curvature points, etc. Right? So, and other applications are image matching or object matching and the animation. So anyway, this is based on the animation only, right? So that means the colon can be stretched with the help of skeletons. So this is one part of the talk. So the second part of the talk, it's based on the traditional machine learning algorithm. All right. So the machine learning algorithm, like for example, we have used the CT data, computerized tomography data, and MRI data. All right. So here we will talk about the brain lesion delineation and classification, right? Hemorrhagic stroke lesion segmentation, right? And as well as ischemic stroke lesion segmentation. So one is based on the CT, another one is based on the MRI images. So here, all right. So if I call the stroke is ischemic stroke, all right. Hopefully I am pronouncing rightly. If any doctors are there, please excuse me. So here, right. So this particular portion, right, is the brain. All right. If the tissue is affected, right. So the blockage will be like this. You are seeing the blockage, right? The blood has to flow through this, but if there is any blockage, so then you will get stroke like this. You call it as a ischemic stroke, right? So another one is hemorrhagic stroke. So here you go, right? So this happens over this side, all right, the skull, and you can see here, right? So there will be a rupture. So this is a cerebral artery. So there will be a rupture. So if there is a rupture, you will get stroke like this. All right, you call it as a hemorrhagic stroke. So now this is the example of CT scan where you can see one is the hemorrhagic, second one is ischemic, and third one is a normal, right? So this is the hemorrhagic stroke, ischemic stroke, and this is the normal case. All right, and similarly MRI. So in the case of one is CT, the first one I have shown CT. The second is this is hemorrhage, and this is ischemic, and this is a normal case, right? So this is in terms of MRI images. So how do we do this work, right? So because we have to do the segmentation, I have to find out, right, the segmentation where is there any hemorrhagic stroke or ischemic stroke, or it is normal, right? So one such approach is the fuzzy C-means clustering. So almost everybody might have heard K-means clustering, right? So it is a usual one, right? Suppose I am, let us say I want to calculate the percentage, right? You add all the marks and divided by the total number of subjects. Whereas in the case of a CGPA system, you are given some weight, right? You are given a weight. Weight is the number of credits. So number of credits into the score that you have got. Let us say A plus means 10, A means 9, all right? So some credit period will be there. Let us say 4. So 4 into your marks, and denominator also that 4 will be there. So in that case, you calculate CGPA, right? You call, I mean, percentage is one system, CGPA is another, IIT and all CGPA. All right. So in a similar way, in the case of fuzzy C-means clustering, all right. So I use, here you have the gamma factor, the gamma square. All right. So this is the objective function in the case of C-means cluster. All right. So we are taking a weight. So the weight you call it as the gamma square. All right. And in fact, this gamma squared is nothing but the distance, Euclidean distance. All right. So this is the distance between the data point and the cluster center. Right. The data points and the cluster center. And Uij we can take like this, right? So that is what it is representing a degree. So this is the coefficient, and here you have the weight Uij of m, Uij power m, which is the weight. Right. So the weight we are considering, like the credit system, you consider the number of hours. Then you are calculating the CGPA. In a similar way, here you have Uij. So that is nothing but the degree of the fuzziness. You call it as a weight, the weighting exponent. Right. So this is between 0 and n. And Uij summation should be equal to 1. So whatever weight you consider, the summation should be equal to 1. Right. So this is based on the fuzzy C-means clustering, and you define Uij like this. So slightly differing from the usual, the distance metric that is being used in the literature. All right. And we slightly modify whatever we are seeing in the previous case. Let us say equation 1, 2, 3, and then the modified distance metric is defined like that. And in the application point of view, the mathematics is coming over here. So here you go. All right. So here the given CT images, right? So given CT images, the column A is the CT image, and then there are several other methods, FCM, SFCM, they are all several other methods. And if you look at the proposed method, the last one is the proposed method. So quantitatively we measure, right? So this is the quantitative measure. Whatever I am talking in the previous case. So quantitatively, the PM stands for the proposed method. So the proposed method is outperforming many of the existing methods. So this is how you can do the segmentation, right? So the last column is the method, the fuzzy C means clustering method, right? So one is for, let us say, CT scan, another one is for the MRI. All right. So here you can see, I want the segmentation. So you have all the method A, B, C, D, E, F up to GH. Okay. So in all the cases, so how this is giving the output. And similarly, here you go. All right. So this is segmentation. This is, so A is the original image, and then several methods, FCM, SFCM, or all the other methods, and F, the last one is ours. Right. So you are given the MRI image like this. So this, you have to segment it out this portion. So that is what the idea. So this is the measure, right? So based on this measure, I can say that, okay, the proposed method is outperforming all the existing methods. So that is what the numerical results, quantitative results. And similarly, we have to do the box plot for different comparisons, right? So one is based on the dice coefficient, Jacquard, right, Osdorff, and the precision, right? Precision and recall aspect. So this is called as the box plot for the various cases, right? So the last one is proposed method, right? So the experimental results are also saying proposed method is outperforming the existing method. Right. So in this case, right, the proposed method case, the average dice coefficient, right? So one of the measures, so which is found to be 0.75. Right. Similarly, other one is based on the random forest. These are all, let us say, 5 years back, right? The researchers have done. In fact, I am explaining from my paper, our paper itself. All right. So this is what the researchers have done, let us say 5 years back, 5 or 6 years back. All right. So this one is based on the random forest, right? The segmentation of ischemic stroke lesion using the random forest. So here, so these are all the basics, right? So how we are dividing, all right? So here you are having the wavelet transformation. So based on the 3-level wavelet transformation, that means 3 times we have to decompose and then reconstruct the image, right? So when you're reconstructing image, the noise will be removed, which is based on the wavelet transformation, right? Based on the wavelet transformation. So once after decomposition, right? So how your image look like? So for example, I mean, I will be given, right, the original images like this, right? Original images like this. So when you find out, let us say, the wavelet decomposition, and then you are going to do the reconstruction, then after reconstruction, what will be your resultant image? That means you have done a pre-processing algorithm. This is the one, right? You have an original image, and here you go, right? So these are all the denoised images. So it's noisy image. So once I use this wavelet transformation and put it back, so you can see that, right? The noise has been removed. So now, when I go for the Bayesian segmentation, right? So this is done on ITK snap data set, right? So in this case, so it goes like this. Suppose I have an image, right? Let us say the MRI, 3D MRI images. So now the pre-processing, as we already discussed, with the help of wavelet decomposition, and you have to do certain thresholding, right? So this is what you have to do. Certain thresholding we have to do. So here it is written. We have applied soft thresholding. Right after getting the wavelet coefficient, you have to do some thresholding. So once I do the thresholding, all right, so we have to find out the image back, right? So the noise part will be removed. You also call it as a denoising the image. and then you apply random forest for training. Right? So the random forest for training, so that will tell, right? It is a binary class, assume that it is a binary class problem. So it will tell, all right? Or even if it is a several classes you want, I mean, you can do using the random forest algorithm, right? So that means this random forest algorithm will classify the brain into several parts, all right? So you have the pre-processed test image, and then from the image, apply wavelet decomposition and do some soft thresholding, get the reconstructed image, right? Apply random forest. So both will give you the brain, right? The brain image into the different parts. And then we are going to have the segmented stroke lesion, right? So this is what exactly the flow goes. And when you apply this particular algorithm, you can see this is the input and this is a pre-processed image, right? After applying the wavelet transformation and the soft thresholding, correct? And you can see the ground truth is this, right? The ground truth is this, and various cases, segmentation using only thresholding method, right? So this is the one you are getting almost, but there are few things are outperforming. You can see even visually, right? So based on thresholding method and based on the random forest, all right? And you can do some thresholding, further thresholding, right? You call it as a overlay, all right? In random forest. So you will get the output like this. So mostly, right, if you look at the last column, so they are matching almost visually, all right? Now, visually, they are matching with the ground truth. So this is the segmentation point of view, right? For the case of CT images, and this is the case of MRI, and you can see, right? So there are several comparisons, and then you can find out, right? So even if you look at with the ground truth, you can find the segmentation properly. So these are all the different approaches. And the last, right? So here you have wavelet plus the thresholding. Sorry, wavelet plus thresholding, right? And wavelet plus random forest, right? The result is outperforming the existing methods. So the basic idea over here is we have used the CT scan and MRI for the segmentation, right? So the different strokes. And this is the second part of the lecture. And the third part, all right? So here I'm going to talk about the brain-computer interface. All right, so brain-computer interface based on the basic machine learning algorithm. All right, so I'll tell you what are all the work my research scholars have done with the help of deep learning algorithms. Right, so here the brain-computer interface. I'll talk about HOG, PHOG, and Eden-Margot model. All right. Wavelet plus Eden-Margot model. So now, what is the brain-computer interface? So, for example, assume that I'm in the hall and I'm seeing several devices. One is a TV, another one is a refrigerator. Sorry, AC. All right, and here you have several. Right, maybe there is a device where you can switch on and off. So we all know that now we are able to control these with the help of remote. All right. So maybe who knows, in another 5 to 10 years, whatever you're thinking, assume that I'm watching one news channel. I want to change to sports channel. Right. Let us say to watch cricket match. Can it happen? Right. Based on your EEG. EEG stands for electroencephalogram. Right. EEG signal. Based on your EEG signal. All right. So right now the apparatus is very heavy. Who knows? In another 10 or 20 years, I mean, you can put that into your mobile. Right? So now I am thinking I want to reduce the temperature to, let us say, 18. Right now it is 23. Assume that I want to set it to 18. Can it be done automatically? Or even I want to switch off the light. Correct? I'm thinking and whether the light can be switched off. Right? So similarly, I want to turn off certain player or turn on certain player. Right? So this is called the brain-computer interface. I'm thinking, can it happen? All right. So here you see the very basic model, the old model, right? 14 channels. This is called the EEG, electroencephalogram device. So here you can see the electrodes. All right. Here the circle in shape, they are electrodes. Right. So here you go, 14 channels. All right. Whereas right now in our lab, we have a 2 to 6 channels. Imagine this is a slightly old model. A 2 to 6 channel model, 2 to 6 channel. It almost look like this when I'm using a EEG device. It looks like this, right? You put and the rounding portion, right? They are all right. So this is what we explained. This is nothing but electrodes. The rounding portions are nothing but the electrodes, right? So here you are seeing the electrodes. Yes, these are all electrodes. So now this is the apparatus, right? So EEG under arrow B. So here we have up to 160 channels, right? As I said, I mean, there is a lab, they have the 250 kind of channel. So right now, right, so you have the device like this, so you can see the complete specification, and here it can support up to 160 channels. The one initially we show, this is 14 channels. So now you can put the device like this in the head and then assume that, I mean, there were several problems solved, right? So one of them is slightly old work, but many are extensively, they are working on the EEG with the several emotional analysis. I'll talk about that, right, with the help of deep learning algorithm. So here, the prediction of advertisement preference by using EEG response and sentiment analysis. Right. So, for example, assume that you are given, let us say, 10 different songs, and then your task is to rank the songs, right? Whichever is very good, put a first rank, and the second rank, third rank, and so on. Whichever is poor will go over the last rank. Assume that you are given like this, right? So this is your EEG apparatus that you are putting, and then you are watching some YouTube or you watching some video, right? Which is a song. So now let us have two different data. One data you are producing from EEG, electroencephalogram. Another one is based on the sentiment analysis. All right. Another one is based on sentiment analysis. Meaning is, let us say in the voting machine, you have EVM, right? EVM, you are getting a data, and another one is ballot. The same, right? So same time you are getting two data, right? Same time. For the same reason, assume that you are collecting or getting two different data, right? Model. I mean to say model, right? Assume that a person is using EVM as well as a ballot at the same time. Correct. In a similar way, I am generating a data. For example, I am seeing a movie. I am seeing a song. So I can my brain signal will give you something based on my mood. All right. I'm watching the song. Okay, the song is really good. Yes, the signal will be different. If the song is very bad, the signal will be completely different from the song is good. All right. So sentiment analysis, assume that I am asking you to note down, let us say in the paper, right? So you can see the song is good, you will mark it something, right? Let us say you are grading it, you will give a grade. A is a top grade. And assume that the song is not good, you will get D grade. So I am getting both the data. One data is based on, let us say EEG, another data is based on the sentiment analysis. Right? It's an opinion. Let us say feedback of a faculty, feedback of an employer. Right? So you are taking two different data. One is, let us say you are watching the video, getting a EEG data. And another one is, let us say, comment data, right? The text data. So you do sentiment analysis on text data, and then, right? So you use the same machine learning model, find out the rating, right? For example, the sentiment data. So let us assume you have the faculty appraisal data, right? You have out of 10 marks, and then you are numerically calculating, right? You can do it. And in a similar way, EEG data, right? So EEG data, you do the future extraction. So, I request all the participants to mute the mic. Somebody has again.
Participants, please try to understand. Sorry, Professor.
No problem, no problem. Because their voice is slightly more. Okay, I'm fine now. Right? So EEG data. Another data is the EEG data. So that will, from those data, we can always extract the features. Right? And then use some analysis. So for example, you want to use a regression analysis, any machine learning model, basic machine learning model, you can get the score. All right. So let us assume using sentiment analysis, I'm getting a score, let us say alpha, and EEG data, I'm getting a score, let us say beta. Now, right, you can do, right, whatever you want, right? Alpha plus beta you want to take, or you want to analyze with alpha beta, you can do that, right? How you are mixing, and then you can able to predict. For example, the same EVM story. I mean, you are checking whether, yeah, it is always possible. You may not get the matching because in the EVM machine, I can vote for one person, and in the ballot, I can do it for another person. But the idea is it matching? All right. So for that, your sentiment analysis will be useful. So for initial stage, the researchers have worked like this, right? Because I cannot believe this EEG. All right. So initially, whatever you are coming up with the invention, you may not believe it first. So for verification, I am doing this sentiment analysis, right? Like taking a feedback. So I am comparing whatever the prediction that I have made, whether it is matching with, all right, matching with my results, what I have taken from the EEG, right? So this is called the multimodal. So when you're doing the fusion, and then the video rating or the songs that can be predicted. Right. So here you go. I mean, this is the EEG signal of 14 channels, right? It goes like this. All right. So the main idea is the signal. I mean, you have to get a green in color, right? For example, this rank, the signal that I have got from EEG, the rank goes 3. 1 is the best, right? Here, complete red, the rank is 5. This is a poor signal. And these are all better, right? Since I am getting more green, the results are better. So this is the brain activity map. And then we have to do the smoothing, right? Signal smoothing. I mean, you can use any filter, like a moving average filter, or I can do the analysis with the help of independent component, right? You follow the independent component analysis. So this is the signal acquired, but after smoothing, your signal should be like this. All right. So in the case of sentiment analysis, let us say you can have several ranks. So one example, binary case, let us say positive sentiment and negative. Right. So you have a training, you can train it and get the output. All right. Or you extract the features and train the data, get the classification. right? So before classification, so you have to again extract the futures. You have to do some pre-processing, and maybe you can have the common data, right? Whatever comments you had given, or you can simply use any statistics, simple statistics, to find out what exactly the class is. All right. So you may have, if it is a binary class, you may have a positive with the score or negative with the score, right? So you may have the analyzer like a naive-Bayes algorithm, right? One of the popular classification algorithm. Right. So this is how we can predict the score, right? That means you are given 10 different songs. With the help of EEG, let us assume which is the best, right? One point of time, you can remove the sentiment analysis. So that is what exactly in India we are doing. We are not believing on ballot papers now, right? The election is going based on only the EVM, right? Last 2-3 elections, I believe. Right. So at one point of time, you forget about the sentiment analysis. You use only EEG. So now what we are doing, we are comparing whether my results are coming closely to your, because the same user, I mean, he is writing in a paper also. What is the rank of this song? You are given a EEG signal also, and then you are noting down the song is the best, song is good. Correct. So at one point of time, I can remove one model, sentiment analysis, and with the help of only EEG signal, so is it possible to predict or is it possible to get the ranks of the songs? And the second one is the brain signal, right, for the user identification and verification. All right. For example, here, I mean, when you're signing, during your signature, I can able to take your signal, right? So when you're signing some documents, I can able to take your EEG, right? So in that case, if somebody is forging, right, during the signature, let us say somebody is forging, if both the signatures are same, all right, so the transaction can happen. This is what presently we are doing, right? Presently the banks are doing. Correct. Suppose I am taking one more data during my signature. What is my mental state? All right. So, for example, assume that you are doing your signature. You are passing a $1 million check. Assume that, right? What will be your mind state? Or you are withdrawing your your signature. Handwriting or signature will definitely differ. Or assume that when you are writing at the last moment of the exam. Initially, when you're starting, you know your handwriting will be really good. But at the last moment, the same word, assume that you are using, same word. All right? You are writing another answer, but the same words you are using, your handwriting will be differing. I mean, everybody practically, we have come across that. Right? So initially, when you start, you may not be tensed, or you can write properly. But let us say you have another 15 minutes more, but you have to complete 3 questions. The same words, whatever you are writing, or even you are signing this kind of period, right? So your signature will also be completely different. Completely means it will change. I mean, you can find there is a change, right? So this leads to, right, this scenario leads to take out, let us say, one more model. Let us say EEG, apart from your signature. So for example, here you are seeing A is a genuine signature, B is the forged one. Right? So can I take the EEG of the person A and person B? Right? So now instead of one, can we use 2 model, and then can you authorize, right, your transaction? So that is what the idea, right? So during the signature, I am taking your EEG, right? So then when I store this, right, when I store, not only, so right now what is bank doing? I mean, it is seeing, suppose you are giving some signature and it is checking whether, I mean, the signature is yours or not. Right? The signature is yours or not. and then the transaction is being happened. So apart from that, if we store, let us say I have a signal, assume that I use the debauches for wavelet transformation. So I will have, for example, the 128 hertz will be divided at 64 to 64, level 1, and then it will further divide. All right, you call it as a gamma signal. All right, so one is the real part, another one is a, or I call it as a low frequency, high frequency. The low frequency component, and 0 to 64, 64 to 128, you call it as a high frequency component. And similarly, the low frequency component is further divided. You call it as a gamma signal. Here, beta, alpha, and theta. Right? So this is the signal. So this is called the wavelet decomposition. Level 1 decomposition, and level 2 decomposition in the low frequency domain, you call it as a gamma signal. Level 3, you have beta signal. Right? Again, the low frequency component you are dividing. Level 4, low frequency component, when I divide, it's an alpha signal and theta signal. All right? So this is based on the wavelet transformation. So given EEG signal, you are having in a frequency domain like this. So now let us say pyramid histogram of gradient, PHOG, and Eden-Margot model for signature, because you have two models now. One is a signature, which is in an image form, and another one is brain signal. All right, the brain signal, which is in one-dimensional form. All right. So for future extraction, for the signature point of view, I use PHOG, which is called a pyramidal histogram of gradient. And for classification, we use Eden-Margot model. And similarly, for the case of a brain signal, I use discrete wavelet transformation. And for classification, we use Eden-Margot model. So this is the initial part of work. Let us take 70 subjects, 40 males and 30 females. In fact, we have done. And the age is ranging between 15 to 55. All right. And then these are all the number of participants. And here you go. The first one is original signature with the corresponding EEG. Second one is, it is a forged one corresponding EEG. And the third one is the original signature, your EEG. And the fourth one is the forged one with the EEG. All right. So now we have bimodal data. One is a EEG signal, another one is an image. So based on this, so when you train your model, all right, with different cases, right? So there is a possibility that you can check only your signature, how far it is authorizing, or both signature and EEG signal, how far you are getting the accuracy. And the last one is only EEG, right? At one point of time, assume that only EEG. What is your accuracy? All right. So here with the late fusion of PHOG with the EEG, using Eden-Margot model, so it is giving up to 98.24% accuracy. All right. So these are all the two different problems I mentioned with the application of EEG signal. So this is the work, right? So suppose in the hospitals or any medical centers, the main idea is you have to secure the image, right? To secure the, let us say, X-ray image or MRI images, right? I should not identify I should not tell the patient, right? Or I should not identify, or one should not identify the patients. So you have to maintain certain, security or secret one. All right. So in that case, how the watermarking, right? So the help of watermarking and encryption is being used. So for example, so let us consider a person, right? So this is the image I want to secure. All right. Assume that this is a person, the person's MRI, maybe some test, and this is the MRI. All right. So now what we can do, I mean, you know what do you mean by watermarking? Watermarking algorithm. For example, you're seeing, let us say, Star Sports, right? So you have the logo. So the logo is the visible logo. That you call it as a visible watermark. Whereas in our currency, the Indian currency, we have an invisible watermark. Right? So watermarking is one area, and another one is encryption. All right. So in the cloud nowadays, right, all the data, most of the data are being stored in the cloud. Right. So in the cloud, I don't want to put my original image, original file. So let us assume I'm encrypting it, right? So you have several encryption algorithms, right? Chinese reminder theorem, using Chinese reminder theorem, or RSA encryption, right? Or you can have a perturbation of binary. So these are all the encryption algorithms. So based on this encryption algorithm, I will put like this. You can see C, D, E. So A is the cover image, B is the secret information. So cover image in the sense I can put this into this image, all right, using watermarking. So I can digitally I can place this A into B. That is the meaning, all right? Secret information. C is nothing but I can make a share. For example, I am using, let us say, permutation of binary or semi secret algorithm or Chinese reminder theorem. I can make many shares. I mean, using the function, hash function. Right? So, for example, you are given one data, I can create, let us say, n number of shares. N number of shares in the sense, each share is nothing but the encrypted data. All right. So now if I put the encrypted data in my cloud, I mean, nobody can see what it is. Nobody should know what it is. Nobody knows what it is. Right. So that my information, even though if they hack, my information will be saved. Right. So the beauty of this encryption algorithm, assume that I am putting everything in a different cloud. For example, three shares. Right. For example, this one C I put in one center. Let us say Calcutta. D I put in another center, Delhi. And E I put in another center. Right. E stands for something. Right. So now from two cloud centers, I can able to reconstruct the image. That is what the beauty, K out of N algorithm. K is strictly less than N. The K out of N algorithm is saying, I mean, you can able to reconstruct. Suppose assume that there are 10 different cloud, but I have only 3 are up, 7 servers are down. Still, I can able to get the data, right? Encrypted data. It is in the encrypted form, not the original form. Original form means nothing. Even one server is up, I can get it, right? But here, the encrypted forms you have in 10 different servers. So if 3 are up, 7 are down, still I can able to retrieve my original data. So that is the beauty of K out of N algorithm. All right. So here you go. All right. So share of the cover image. So C is nothing but, so from the cover image, I can able to get this share, one share, and D and E shares containing only cover image information, right? So C contains share of cover image embedded with secret information. Okay. So assume that I put A over here using watermarking, and that particular share is C. And D and E are nothing but shares of only cover image. That means the MRI image. Right. So now I can able to retrieve. So only MRI image I can able to get it. Right. And based on this share, I can segregate this MRI image and a person. Right. So that is what the result is being done. So the main idea is, so B is the person, A is the corresponding, right, image, right, which is saying that what kind of disease the person is having, right? So now in my cloud, I will have, right, the information like C, D, and E, right? It is of the form C, D, and E. So I cannot make out anything. Whereas the C, D, E contain the information of the person and the corresponding image, corresponding the medical image, right? So now I can able to retrieve this. I have this data in my cloud, but these are all the secret information. From this secret information, I can able to make out who are they, right? So this application, right, in particularly medical imaging application. So extensively we have done several encryption algorithms, right? So these are all, right. I think I have not, okay. In fact, if you go through my website, so you can find several algorithms, right? So we have done in the case of encryption and in the medical imaging point of view, right? Medical applications point of view. So this is the application that we have done. And in fact, this was published in MIPR long back, right? So now recently, still I have 2019, 21, I have 9 minutes more. Okay. I'll just go through the overview. So this talk recently I had given in AIMS Rishikesh. So how this artificial intelligence, right? So is useful in lung cancer screening and therapeutics. So in fact, the medical point of view, they call radiomics and radiogenomics. So which is nothing but feature selection and feature extraction in the artificial intelligence point of view. All right. So this was the outline of my talk. So the cancer treatment using AI. In fact, we have done for different cancer. And in the lung cancer, how the machine learning approaches and deep learning approaches were being used. So in fact, so we have done, right, the AI-based cancer detection. So one is for a skin cancer we have done. The first one is skin cancer, and that was published in IET image processing. And then brain tumor classification, right, which was published in ASEM transactions on internet technology. Again, we had a brain tumor segmentation. So here it is a segmentation, which has appeared in MTAP 2022. Then we had a skin lesion segmentation. This also we have done. In fact, I talked about, I did not talk about skin lesion. I talked about the hemorrhage, right? So this appeared in biomedical signal processing and control, skin lesion segmentation. And the last one is a breast mass segmentation, right? The European Signal Processing Conference, USIPCO, right? So these are all the AI-based technique, right? The machine learning or deep learning based technique we have done for cancer detection other than the lungs. All right. So similarly, here you have the breast cancer point of view, right? The first one which appeared in the Journal of Digital Imaging. Then again, segmentation of skin lesion, MTAP 2024. Skin lesion, computer vision and image processing, CVIP conference 2021. And here you have ICPR, very recently, 2022. We had a skin lesion classification. And in the MICAI workshop, one of the core A-star conference. So in that core MICAI conference, we had a workshop, multimodal learning and fusion across scales for clinical decision support. All right. So where we presented skin lesion classification. So these are all the literature kind of. In fact, we have done for other cancers, right? Whereas I have correlated some of the techniques where the machine learning and deep learning were being used for the lung cancer. All right. So for the case of screening and early detection, all right, so the CT scans are being used, right, with the help of the basic machine learning or AI-based model. Whereas with the help of convolution neural networks, the DL based model, all right, that is also being used for screening and early detection. And for the risk prediction, there are several ML algorithms, machine learning algorithms. For the lung cancer is the initial prediction, early detection and screening, and the role of AI will be applicable in the risk prediction also. Similarly, treatment personalization, all right? So AI is being useful, and also many ML and AI driven based algorithm are useful for the drug discovery, and also in the case of the treatment monitoring. So this is the deep learning model where, for example, here it is a patient screening. The data is being collected, and whatever data you have collected, the noise is being removed. All right. So in fact, I talked about segmentation, right, for brain hemorrhage. In a similar way, right. So we have to use some segmentation model and get the segmentation output. All right. And what we have to do here. So once you have the segmented output data, this is a segmented output data, use the convolution neural network. Right. So this is the convolution neural network that is a deep learning based. Right. So this is a deep learning based algorithm. And here, right. So that will give you the malignant or benign tumors. Right. So whether the patient is suffering from cancer or not. So that is the final prediction. So where, I mean, here, once you get the segmented results, right, the convolution layer, that means CNN is being used, and then it is useful for predicting the results. Right. So AI. So in the case of post-therapy monitoring, right, from screening to post-therapy monitoring, so the flow goes like this. So you have it is AI is useful for cancer prediction, cancer screening, all right, and the cancer surveillance. So all this, the AI is playing a vital role, right? And here the case of radiogenomics. So the radiogenomics is nothing but you are extracting the features, right? So once you are extracting the features, so those features based on the RNA, right? So based on RNA here, it is called a radiogenomics gene. All right. So here's the usual one, the CT images, and then you do the identification or finding out the semantic features, and here you have, right? Here you have a data based on the CT images, and you have a RNA. Another, in fact, we have seen several bimodal problems, right? Bimodal and multimodal problem. So here you have a RNA sample. So from the RNA sample, assume that, right, I am doing certain the medical task, right, the sequencing or genome reference, right? So then I apply the machine learning, let us say clustering, all right, the clustering for different patients. So I have a data of the patient, let us say CT images, and the corresponding, let us say RNA. So now it will be like a bimodal. So one is based on the CT image data, and another one is based on the RNA data, and then, right, I can have the statistical correlation between the CT image data of the patient and the RNA, right? So this you call it as radiogenomics, all right? And then this is the mathematical, right, the complete mathematical model. So one is let us say based on, assume that support vector machine, all right? The second one you can find out using logistic regression. So we can apply, right? So we can apply random forest, we can apply gradient boosting machine, or gradient boosting algorithm, etc. Right? So basically, when you are given an image, let us say after image acquisition, pre-processing, let us say segmentation. After segmentation, we have to extract the features and apply the machine learning algorithms and get the output for the cancerous and non-cancerous classification. So it is a binary classification, right? So very recently they are using, because I mean these data for them, right, it is available, the radiogenomics data, right? So for example, they have a CT images as well as RNA. Still, even 2023, this paper was there in 20. It's all literature paper. So they are still using the basic machine learning model, or they are using very simple deep learning model like this. Yeah, so again, this is another approach. So here you have, right, so convolution layer, max pooling. So and then you are getting this one. So this is a given input shape. So here you have, right, up to here you are going a sigmoid, dense and flatten. So this is based on the deep learning algorithms. Correct. So the main idea is, so this is one, and the main idea is you have input data. You have to do the image pre-processing, and once I get the isolation, this is a lung isolation, then I go for the deep learning algorithm, right? So once you get the tumor, once you segment the tumor, apply the deep learning algorithm and get the output data. So this is also, right, in fact, it is published in Nature Communications in 2022. So why I am focusing here, right? So these kind of data, the radiogenomics data, or the case of lung, right, the lung cancer. So the deep learning algorithms are being used. So these are all the some literature. So this will be useful, right? So here in this particular talk, so I had given very recently in AIMS Rishikesh. So how AI models or deep learning models are useful in predicting or the early stage of the lung cancer. Okay, so if you have any questions, I mean, we can discuss.
Thank you, Professor, for your valuable time, and it was a very interesting section. Those who are really working on image processing, especially medical image processing, they are really benefiting about this lecture. Due to running out of the short time, actually,
I'll just conclude.
Yes,
I'll just conclude.
Yes, Professor. Yes, Professor.
So, right now, I mean, if you see my website, there are several PhD students have done with me in medical image processing, and they're in a very good position now. One, she is doing a postdoc in the US. Second one is a faculty in IIIT Allahabad, and there are many. I mean, I know 4 or 5, or even more than that, they have done in medical imaging. And I thank, several funding from these government and private organizations. So I have 2 labs. If you happen to visit Roorkee, right now I'm in Chennai. So if you plan to visit Roorkee, please visit my lab. And we have Divya Sampak. I'm a chair professor of Divya Sampak IIT Roorkee. So you can, those who are those who want projects, or you are coming up with some products, so they are supporting. You can go through the website tahiitr.ac.in. I have Divya Sampak. And if you want to know about my research group, in fact, you can see the QR code. You can see all my students, alumni as well, those who have done a work in medical imaging. And this is my website, and this is my email ID. So you can contact me at any time, and you can go through my website as well. And with this, thank you all. Thank you.
Professor, if I can make a comment, because your talk, which I just, I see, dziękuję, that I just looked into the last few slides. You may want to stay. I know that you are extremely busy and it's time for the dinner, but you may want to stay a little bit for my talk, because as a matter of fact, I will be using some of the thoughts from your talk, and because I'm going to be talking about frugal artificial intelligence, which also applies to image processing. So I would like to warmly invite you to spend a little bit of time looking into what I'm going to be talking about, because I think
you're going to talk now?
Yes. Well, at least I hope so.
Professor Balasubramanian, I'll introduce you to our next speaker, Professor Marcin Pepazaiki, and Professor Marcin, Professor Balasubramanian from IIT Roorkee